Hi everyone, welcome to week 9. We're going to continue with our work on application of integration. Um, we've already seen how to find areas and volumes using a particular method. Today we're going to learn how to find volumes by what is called cylindrical shells. So first of all, motivation, why learn something else? Here's the idea. Let's say you have this particular function, y equals 2x squared minus x cubed. If you and and you rotate it on the y-axis and you form a solid. Horizontal slices are a problem because you don't know, for example, it's not symmetric, so you don't know exactly what the expression for each end of the function is, right? And then using horizontal, vertical ones are a problem because it's a cubic and it's difficult to solve x in terms of y. So in these cases, what we do is we use a method of cylindrical shells. Now, what is a cylindrical shell? It's a hollow shell um, with a radius, say R2 and R1, and then the difference between their radius is the thickness, which is R2 minus R1, and this height is set h. Yeah. So the volume of the inside, right? What's enclosed in here, this volume can be found by subtracting the outer volume pi R2 squared h minus pi R1 squared h. And then we do a little bit of clever math. Um, this is the difference of squares, can be written as R2 minus R1 times R2 plus R1. Noticing this is the sum of the radius, I divide it by 2 and multiply by 2 um, and let R2 minus R1 be delta R. Then I can say that R1 plus R2 over 2 is the average thickness of the shell. Then the volume becomes 2 pi R delta R h. 2 pi R is the circumference, h is the height, and delta R is the thickness. Now, let's try to translate this to, say, a given function. Let's say this is my function, f of x, and then I am rotating this to form a solid. So there's a little bit of a hole here in the solid right there. And these are the x values, and they go from A to B. Okay, so if I use the formula that is given to me, what I'm going to find is that for each of these, that's a shell right there, right? It's going to be a tiny shell. This thickness is going to be dx. The circumference, if you see um, the height is the value of the function, which is f of x. And the circumference depends on where we are. So if we are at x, the circumference is 2 pi x. So what we get is that the volume becomes 2 pi x f of x dx. And then if we sum over all of these thin shells, then we get the volume of the whole thing. And that can be written as the integration of 2 pi x f of x dx, going from A to B. So that's the method of finding this volume by shells. So here's what you get. These are the terms. You can use this space to sort of derive it again. Now, what you can also visualize it. You can also visualize it as, if I take this and then I cut it here, and then I open it. If I cut and open it, what I'm going to get is I'm going to get this long strip with a particular thickness. Yeah. And what we're saying is that this thickness is delta x, the height is f of x, and this length here is 2 pi x, which is the circumference. Right? So the volume is obviously length times width times height. Okay, let's look at one example. Find the volume of a solid obtained by rotating about the y-axis, the region bound by the exact equation, which we said was a problem for us, right? So step one, let's see the graph of this function is something like that. right? So if you factor out, you see this is x squared 2 minus x. So 0 at x equals 2 and x equals 0. So we start making our shell. Um, that's something like that is going to be our shell, right? Right here. So again, as you can see, the height is f of x. Now, if this is at any distance x, then the volume is 2 pi x f of x, which is 2x squared minus x cubed dx, integrating from 0 to 2. Well, that is 2 pi, then you have 2x cubed 0 to 2 minus x to the 4 0 to 2 dx. That's 2 pi 2 over 4 x to the 4 0 to 2 minus 1 over 5 x to the 5 0 to 2. Now that's 2 pi 1 half times 16 minus 32 over 5. That's 8. 8 times 5 is 40. That's going to be 2 pi 8 over 5, which is 16 pi over 5. And the next example, we have to find the volume of a solid rotating about the y-axis, the region between y equals x and y equals x squared. So let's plot y equals x is a line through origin of slope 1. Y equals x squared also goes through the origin, but along with that, it let's amplify it a little bit. This point is 1 comma 1, and that's because x squared equals x gives me x minus 1 equals 0, giving me x equals 0 and x equals 1. And when x equals 1, y equals 1, right? So this is what we are rotating now. Now, over here, if I consider a shell, right, then the height of the shell, this is what is happening, it's being rotated. Sorry, my diagram is not very nice. But this height here, the height is actually going to be x minus x squared. Right? At any distance x, then the volume is 2 pi x. Now instead of f of x, it's going to be the top one minus the bottom. X minus x squared dx, and it's going to be from 0 to 1. Which again, when you solve, that's going to be 2 pi x cubed over 3 minus x to the 4 over 4 from 0 to 1. And that's 2 pi 1/3 minus 1/4, which is 1/12, giving you pi over 6. That's the end of this video.